It is well known that ants are exceptionally strong and fast. Although estimates vary, the average ant can carry between 10 and 50 times its own body weight, and run at approximately 300 meters an hour, a rate of nearly 800 times its body length a minute. This is equivalent to the average Western man carrying between 850 and 4,500 kg, 4.5 tons, over his head, and running at a speed of 83 km or 52 miles per hour. If ants can do it, why can't we? The calculation above is essentially redundant, because a human-sized ant wouldn't be able to travel at 50 miles an hour. In fact, it wouldn't be able to run at all, its legs would crumble under the weight of its own body. In fact, the human-sized ant would have been dead long before it tried to run, because the supply of oxygen to its organs wouldn't have been sufficient to keep it alive, even for a second. The reason that ants are comparatively so strong and speedy for their size relates to the issue of scaling. Surface area does not scale proportionally with volume. For every unit increase in the size of something, surface area increases by length 2, but volume increases by length 3, meaning that the surface area to volume ratio decreases. This is important, because the ratio of outer surface area, e.g. skin, to total volume, e.g. the body, is a significant quantity in biological terms. For example, most vertebrates use lungs to obtain oxygen from the air, because this organ has an exceptionally high surface area to volume ratio, meaning that very large quantities of oxygen can be absorbed. Smaller animals, such as insects, don't have lungs, but instead use a series of connected tubes, called spiracles, to collect oxygen from the air. Spiracles have a much smaller surface area than lungs do, but because insects are relatively small compared to vertebrates, spiracles are quite capable of serving the oxygen requirements of the body. Scaling down even further, bacteria don't need a specialized oxygen collecting mechanism at all. They are so small that they can survive on just the oxygen that diffuses through their outer membrane. The point of all this is, if you were to scale up an insect, in proportion to its current size, its surface area to volume ratio would be drastically altered. An ant scaled up to human size would still be trying to use spiracles to breathe, but their surface area would no longer be sufficient to obtain enough oxygen from the air, and the ant would suffocate. Even if you could deal with this problem, the ant's legs would have suffered from the scaling issue too. The strength of a leg is proportional to its cross-sectional area, and the load it must carry is proportional to the mass of the animal. As size increases, the cross-sectional area would increase in proportion to length 2, but the load would increase with length 3, and the legs would very quickly be too weak to support the animal. Large animals deal with this by changing the shape of their legs. Notice that an elephant's legs are much shorter and wider than an antelope's. Finally, the issue of strength is similar to what we just discussed for legs. The strength of muscle depends on its cross-sectional area, whilst body weight is proportional to volume. Thus a small animal can lift many more times its own body weight than a large animal, because as the size of an animal increases, its muscle strength increases by length 2, but its body weight increases by length 3. Of course, this logic also works in reverse. An ant-sized human would be exceptionally strong and fast, and would have almost boundless energy, since he would be able to take in vastly more oxygen than is needed to run his body. As I'm sure you can guess, he would suffer from other problems though, such as increased heat and water loss, which would almost certainly kill him, although perhaps not quite as fast as the human-sized ant would die.